This is section 8.1 from your class notes, and I'm going to be doing page 2, and the title is Modeling with Differential Equations. Differential equation is an equation involving one or more derivatives of an unknown function. The order of a differential equation is the order of the highest derivative in the equation. So in example 1, these are examples of differential equations of different order. And so if you look at this first one here, dy dx is equal to 3y, so here is a derivative, and since this is the first derivative, the order is 1. In this one, you have a second derivative combined with the first derivative and then the function, and so the highest derivative is 2, so the order is 2. And this one, notice they're using a different variable. So instead of dy dx, this is dy dt, but it's the similar concept. So this has the third derivative with the first derivative, and so the order would be 3. Now for this one here, instead of using dy dx, they're using a y prime. And so it says y prime minus y is equal to 2e to the x. So this one is not as explicit of whether this is a dy dx or a dy dt. So the way that you'll know that this is a dy dt is because of the variable that is used on this right hand side, and the order is 1. For this one, you have a y double prime plus y prime is equal to cosine of t. So since they have a second derivative, the order would be 2. And the way that you can write it using the other notation is dy dt, since t is on the right hand side. Finding solutions of differential equations. A function y is equal to y of x is a solution of a differential equation on an open interval if the equation is satisfied identically on the interval when y and its derivatives are substituted into the equation. So for the first example, what you're going to be doing is you're just confirming that y equals e to the 2x is a solution for the differential equation dy dx minus y is equal to e to the 2x. So you'll first of all have to find the derivative. So here is the derivative, and I got that from here. So if y is equal to 2 or e to the 2x, then taking this derivative with respect to x is dy dx is equal to, just using the chain rule, it's 2e to the 2x. Okay, so now I'm just going to substitute this back into my original differential equation here. So I just rewrote it, dy dx minus y is equal to e to the 2x, and then I'll do my substitution. Okay, so dy dx is what I found here, so that will be 2e to the 2x, and y is equal to this, so that is e to the 2x, and then it says that it equals e to the 2x. Okay, so then you're setting it equal to e to the 2x, and then you simplify on the left-hand side, and you get 2, your e to the 2x is equal to e to the 2x. Okay, so if you take a look at this problem, this is not the only solution for the function. So for example, if you have y equals e to the 2x plus c e to the x, that's also a solution for the differential equation. So we call this as a general solution. So when you have a general solution, it's when you have some constants with it. So you'll have c, sometimes if there's more than one c, they'll call it as c1, c2, c3. So the general solution, it produces a family of integral curves corresponding to the different possible choices for the arbitrary constants. So here's a graph that shows some possibilities. Okay, so this is the integral curves for dy dx minus y is equal to e to the 2x. So you can see that it is basically a vertical translation, right? So if c is equal to 0, then it's this graph right here. If c is equal to 1, then it would be this graph. If c is equal to 2, it would be this one. If c is equal to -1, it would be this one, and so on. So many times you'll have to find what is the general solution, and then if they give you a particular point on the graph, then you're able to find the particular solution. Right? So we'll be going over that later.